coming. And so let's get started on the talks. First up is Matt Shepard. He's going to be making an overview of meson spectroscopy.
Is this working? Why is it turned on? Yeah, good. All right. Okay, so I'll provide some background noise while you configure your virtual machine and download the files and everything. So, Paul asked me to give an overview of meson spectroscopy, and that was kind of a tall order, so I hope this delivers a little bit. I thought it'd be good to kind of start at the beginning, so talk a little bit about QCD and what we're trying to learn in meson spectroscopy. And it's really great that Joe is going to talk after me, so he can correct all the things that I misstate about QCD and what we're going to learn about meson spectroscopy. So QCD in the standard model, why is it interesting, and what can we learn by studying the spectrum of mesons? So we know that empirically, hadrons seem to come in arrangements of mesons and baryons, 2-quark or quark-antiquark mesons and 3-quark baryons, and that's just a fact that we sort of see in nature, and we attribute that to color and the color interaction and QCD in the standard model. And what I want to talk about a little bit is what we might learn about QCD by looking at the spectrum of these mesons, and in particular, there are interesting things to learn about baryons too, but I'll focus on mesons. So it's important to think, why you're doing this, why you're looking for hybrids, why build GlueX, why would you want to look for hybrid mesons, and what do you hope to learn? And I think I like this because it's an example about how studying the spectrum can actually tell you something about the fundamental theory. And so a lot of the motivation for color and introducing color charge in QCD came about by trying to explain this state in the quark model, where you had 3 quarks that all appeared to be the same and all in the same spin configuration, but these are 3 fermions, and they can't be all in the same in the same state, and they have to have something different about them, and the way that you make them different is to give each of them color. And so this was a lot of motivation for having the idea that quarks were colored, and they come in 3 different types, 3 different colors, red, blue, and green. And we see evidence for that now throughout, really, and that's a real central part of QCD, which I'll get back to in just a second. But you see lots of evidence that this is not the only piece of evidence for this now. Here's definitely a more modern piece of evidence, so-called color suppression in decays, where you have, say, a B meson that's red and anti-red, and then if you have this internal type decay to d pi, this quark here has to be, if this is red anti-red, this quark has to be anti-red. It can't be anti-green or anti-blue, because then you wouldn't have a color singlet up here. And so only one of 3 types of quarks will work when the W turns into QQ bar, whereas down here you can have any of the 3 types of quarks. And so this amplitude you expect to be 3 times bigger than this amplitude. All the other CPM elements are the same, and when you make the amplitude 3 times bigger, you get a rate that's about 10 times bigger, and that's about what you see here. So here's a good piece of evidence for color. So why is color interesting? In QCD, you have these 3 types of color, and one thing that you want to do is you want to have gauge invariance. So you want the QCD Lagrangian to remain completely unchanged under transformations in this color space. And if you want to preserve that gauge invariance, then the way to do that is to introduce interactions in Lagrangian that look like quark gluon vertex, or 3 gluon vertex, or 4 gluon vertex. And these are the types of interactions that make QCD really interesting, right? The fact that the gluons can interact with each other. And so in a way, the presence of these interactions, the source of those comes from the idea that you have color and that you have gauge invariance in the QCD interaction. And the fact that you have color in some sense was motivated by trying to explain the spectrum of mesons. So you go from looking at the spectrum of mesons to learning something about the fundamental theory, and then when you have the fundamental theory, you say, well, gee, I have these types of interactions. How do they manifest themselves in the spectrum of mesons? Can I have glue balls, because gluons will stick together, or can I have hybrid mesons? So it's sort of interesting to think about the interplay between spectroscopy and also what we're learning about fundamental QCD in this context. And so why are these types of vertices interesting? Because when you look at the interaction between a quark-antiquark, So in QED, you'd have like just a screening effect, a vacuum polarization effect. And in QCD, you have something like that. You get a quark loop, but then you also have these gluon loops. And these actually produce an anti-screening effect that makes the force really, really strong at larger distances. And that's what results in, ultimately, we think it results in confinement. And the inverse effect at low scales is asymptotic freedom. And so all this emerges from again, rooted in gauge invariance and the fact that you have 3 colors in QCD. And it's interesting to try to understand then what QCD predicts about the spectrum of hadrons. So the unique thing about QCD, as I said, is that the gluon-gluon interactions are there. So gluons can interact with each other, and that results in the way that the coupling constant runs. We know that this generates a significant amount of the mass of the nucleon. We know that makes it a difficult theory. It's non-perturbative. It's hard to calculate. And a lot of those things mean that at low energy, we really must study QCD through hadrons. So what we have are these examples of solving QCD, I guess, which are hadrons. And we have to look at those and try to understand what they're telling us about the fundamental theory of quarks and gluons. And one interesting thing is that if you look at the QCD Lagrangian, it's kind of hard to, on the grounds of the Lagrangian alone, say that, well, I should only have quark-antiquark mesons and I should only have 3 quark baryons, which is what we seem to see dominates nature entirely. So in principle, I could be able to make glue balls, gluons stuck together. I could be able to make quark-gluon hybrids. I should be able to make tetraquarks and pentaquarks and all kinds of good things. None of that seems forbidden by QCD. And so understanding how these complex objects, or how matter effectively emerges from this fundamental theory, is a lot of why we want to study the spectrum of mesons, to get insight into how we build hadrons from the fundamental theory of QCD. So again, pictorially, these other types of things can certainly exist. This seems to satisfy what we know about QCD and the interaction, that you have a net colorless state, as does this one, as does this one. So my convention in drawing these funny little pictures is that this is like red anti-red, so whatever's on the outside is the anti-color, and that helps when you have gluons because they're combinated. This is like blue anti-red gluon, and a blue anti-red gluon, and a red anti-blue gluon. Gluons are in the color octet. And so a big question is, do these things exist, or is there something that we don't understand about the QCD interaction that sort of prohibits these sorts of things from existing? And that's why we build experiments like GlueX to understand more about how hadrons form from QCD. So goal, understand what the QCD Lagrangian is telling us about the rules for building hadrons. So it's an equation, but it's not a very easy equation to interpret or an easy equation to calculate, as Joe will tell you. And can we get any more insight and understanding about what it tells us for making matter, or stable states like mesons? And we can do this by studying the spectrum of mesons. You can also do this in many other ways. You can do this by studying the structure of baryons, by looking at the baryon spectrum, and lots of other areas of hadron physics are dealing with other ways to understand what QCD is telling us about proton structure and those sorts of things. But what we're going to do, and what I would like to highlight really, is looking at patterns in the meson spectrum as an attempt to understand this. So look at sort of the gross features of how all these particles emerge from QCD. And so one component of that is the constituent quark model. This may have been the root of what eventually turned into QCD. And that was this idea that you could put mesons together from spin 1/2 quarks. So you had these quarks of different flavors, and they had constituent quark masses, and you would put them together in various combinations, and you could build the entire spectrum of mesons. So you could take spin 1/2 quarks and combine them, and you could make a state with total angular momentum that was equal to the sum of the orbital and spin components of the quarks, and parity and charge conjugation. And there are rules for how you would combine 2 spin 1/2 fermions in such a way, and you could compute these things, J, P, and C. And it turns out that these are things that you can all measure in experiment. You can measure the total angular momentum of a state that you produce, its parity, and its charge conjugation. And then the big question is, does the spectrum that you calculate from all permutations of putting quarks and antiquarks together in this model agree with what you see in experiment? And if so, that's obviously evidence that this is a good model for how you would build hadrons. And as an example for how that works pretty well, I'll show you the charmonium spectrum. So here's the charmonium spectrum. So you can do an experiment. You take an electron and positron, and you collide them together with a center of mass energy equal to the psi 2s here. So just above, so this is, I think, 3686 MeV, if I remember correctly. And so electron and positron collides together with that energy, and then build an electromagnetic calorimeter and look at the inclusive photon spectrum coming from production of psi 2s. So this is not that different than looking at atomic spectra or something with a spectrophotometer. And there are lots of transitions with photons you can have in the spectrum. So you can have the psi decaying by photons to the chi states. These are p wave states, and down to the eta states, and you can have transition from the chi states to the j psi. And when you look at the photon spectrum, you see all those things. So you see peaks for these three transitions. You see these are three peaks here all lumped together from these three transitions. Here's a peak here from this transition. And this pattern that you see here matches what you would predict if you just take a quark, a charm quark, and a charm antiquark, and you put them together in various combinations of spin, angular momentum. You would get basically this spectrum, and the various spin-orbit interactions and spin-spin interactions give you the splittings here. And the key thing is that you see everything you would expect to see. So you see everything that you could see in transitions from a photon. You don't see anything else, and you don't see things that you wouldn't expect to see. So you can't see a photon transition here to this state because it would violate parity, and it doesn't show up anywhere in the spectrum. But if you look at pi0 transitions, you can find that transition. And you see them in relative rates. So you see the transition to the chi-C states is really big, but the one to the eta C is suppressed, and that has to do with the orientation of the charm quark spins. So everything about this model of putting two spin 1/2 particles together agrees exactly with what you see in this experimental data, and there seem to be no extra features anywhere. So that's kind of evidence that this works. And the thing, I mean, it seems completely obvious, but the key point I want to make here is that patterns are essential, right? So if I gave you any one of these states in the spectrum and you measured the transition to that state, that doesn't really tell you so much about the constituent quark model. It's the fact that you see all of these collectively and their spacings and everything, I think, is what really solidifies the picture that the constituent quark model works. I think that thinking about that is relevant when it comes to thinking about hybrids in the light quark spectrum, because what we have now is instead of an experiment that we do a calculation of QCD, which Joe will talk about, and look at the spectrum that emerges from that calculation. And here, sort of like here, you can sort things by JPC, total angular momentum, parity, charge conjugation, and mass on this axis. And you see a spectrum of states. And this spectrum is a lot more complicated because now instead of just charm, anti-charm quarks, you have up, down, and strange quarks. And you can make lots of different combinations. And one thing that you see in this spectrum is you see a pattern of states here that have exotic JPC. That means they have JPC that you can't make with just a quark and an antiquark. And it turns out the properties of these states are also, they have common properties with some of these other states that are mixed in here. And that is that they look sort of like hybrid mesons. So they seem to have a large gluonic component in them. And so then you can kind of do the same thing that you do with the charm spectrum. You can say, well, now I want to understand this. Let's come up with a picture that gives me this particular pattern of states. And if you want a picture that does that, so here would be the quark-antiquark state. And so this is a conventional meson. And now if I want a nice picture that gives me what hybrid meson would look like, I have a quark-antiquark in some color octet pair. And then I attach this gluonic contribution. So it's some gluonic field or something, and it has JPC 1 plus minus, and it has a mass of roughly 1 to 1.5 GeV. So just like I would have constituent quarks with heavier masses, I could say this is my gluonic contribution to mesons, and here's its mass and quantum numbers, and I just combine that with all combinations of quarks, and that does a really good job. Actually, I should just go forward a slide, reproducing this spectrum here. So this is the type of thing that we wanted. So this is obviously all in calculation, right? This is all calculation of QCD, and this is a spectrum you see. And this is an understanding that you see. But it'd be nice to have this understanding about nature and not necessarily just about a calculation of QCD. And so that's really the point. Understanding the pattern is essential. So I think finding one particular hybrid is not, that's great, it's exciting, but the pattern is what we really, really need to understand what's going on, to claim that we understand what's going on. Okay, so what can we measure about a meson that informs us about its place in the spectrum? So spectra are important because spectra have patterns and things like that. So we can measure mass, JPC, charge, production, and decay tendencies. And I thought I would just give you some examples about what we might learn from these sorts of things. So obviously mass and JPC, if you can measure them, then you can put a bar on this particular plot, right? And you know, you pick the column JPC and then you go and you put a bar there and that's good. And you keep doing that for lots of things and you're going to get a pattern eventually. So how do we go about measuring some of those things? So if we want to measure J, we want to measure the total angular momentum of a state. Here's a simple example. If you wanted to measure J of a rho meson, you would, whatever angular momentum the rho meson has must be carried away in orbital angular momentum of the pions because the pions are spinless. You can look at angular distributions of this decay, and based on those angular distributions, whether they're flat or how many humps and bumps they have, you can conclude what the total angular momentum of the rho meson is. And this was done a very long time ago. And the fact that the rho has J equals 1 and has a certain mass kind of, gives it its place in the constituent quark model as that of two like quarks or up and down quarks with their spins aligned and no relative angular momentum between them. So just total spin 1 and J equals 1. And you see that also in the spectrum right here, rho, the blue. Of course, in reality, that's a little bit more complicated than that because often things don't decay into two spinless objects. They decay into many other things. And so one, I should say also you can measure P and C by looking at the various products of how they decay. So parity is often constrained by the parities of the decay products and the relative angular momentum, and charge conjugation by the various decay products also. So just to give you a more complicated examples, we can look a little bit at some of the evidence for the existence of this state, this exotic 1- state. And so here again, you're looking for an object that decays with a particular angular distribution that's characteristic of 1-. And so what you might do is look for the decay of pi 1, the 1- to rho pi, and the rho decays to pi plus pi minus. And when you do that, you have to be able to separate out all the various contributions, all the things that can decay to rho pi. And so if I just plot the 3 pi and invariant mass, I see bumps in the spectrum that come from both rho pi and f2 pi, the a1, a2, the pi 2. And then by fitting this spectrum using a technique called amplitude analysis that we may get talked about a little bit more in the course of this workshop, although this is kind of at a higher level beyond, I think, the initial analyses that we're going to do with GlueX. You can separate out the contribution of the 1- rho pi amplitude from this spectrum, and you see it's kind of like, it's a little bit of like a needle in a haystack. You have this little contribution here that's small. You can read the axes on the scale of the whole thing. And then you have to interpret this contribution, whether that is a resonant hybrid or not. And that's interesting. And you might try looking at another, this is a needle in a haystack. You could look for bigger needles. Here's an example of a little bit bigger needle. So if you look for a different decay mode of the pi 1 to eta prime pi, this is nice now because it really is a two-body decay to two spinless particles. And you can show that if these things have relative angular momentum 1, that is, they're in a p wave, then this thing must have exotic quantum numbers. And in fact, you see a big contribution of p wave here. And so that's interesting. So there's definitely a huge p wave component to that. And I think that making the next step and interpreting this as a hybrid resonance is also interesting and an item up for discussion a little bit. So these are the types of things, analyses that you can do to try to measure angular momentum. So it's measuring the angular momentum of a state and measuring its spin and measuring its parity. And then there's a step beyond that, I think, which is figuring out what resonances actually contribute to those. I think probably hear maybe some of that tomorrow. Okay, so this is measuring spin, parity, mass, those sorts of things. Some things are easy. So sometimes you can just measure the charge of a state. So measuring charge is actually really easy for experimentalists to do. And sometimes the charge itself is interesting. And here's an example where the charge is interesting. So if you look at collisions of e plus e minus to pi plus pi minus j psi, and you run it at a high center of mass energy, E plus E minus around 4.2 GeV, and you look at the pi j psi system. So this has net charge 1. You see, and this is done by 2 different experiments, the Best collaboration in Beijing and the Bell collaboration. You see a peak in the spectrum here. And so that looks like a state with charge 1 or minus 1. And that's really interesting because it's heavy. It's really heavy. It's about 3.9 GeV. So in order for it to be that heavy, it has to have a charm and an anti-charm quark in it. If it has a charm and an anti-charm quark in it, that would be net charge 0. So the fact that it has net charge 1 means that must have some other quarks in it too. So whatever's going on here, there has to be at minimum 4 quarks involved in this type of interaction. And then, of course, the next layer is trying to interpret what that means. Oh, and I'm missing the slide after this. Darn. Okay, well, what does that mean? Does that mean that it's this compact tetraquark object, or does it mean that there's a neutral meson and a charged meson that are interacting with each other or something? And again, that's an active area of discussion now. But here's a case where measuring charges is interesting. And again, in all this, I think the thing that ultimately has to happen is you need to establish patterns amongst all these states and try to understand what they're telling us about the spectrum. Okay, so you can also look at decay properties. So here's going back to the light quark mesons. Here's another nice example. So here's if we zoom in on the 2++ column here. So this is total angular momentum 2, parity plus charge conjugation plus, and we see predicted from lattice QCD that there are 2 states here, two isoscalar states. That means that they're isospin 0 states. And one is almost all non-strange. That means it's a black bar here. One is almost all strange. You see in other places there's a mixture of green and black bars. But in this case, it turns out that QCD predicts that these 2 states should be separated. One should be purely strange, the other should be non-strange. And it turns out that we have candidates for these 2 states, the F2 1270 and the F2 prime 1525, and we can look how they decay. And one way to look how they decay is to look at decays of charm mesons. And this is a very handy tool because when you have J psi, this is a charm anti-charm state decayed to gamma pi 0, the only quantum numbers you can populate in pi 0 here are 0++, 2++, and 4++. So when I go to this spectrum, I can forget about all of it. And I know because 0++ isn't drawn here, but I know that I can just focus on the 2++ part. And I don't have to worry about backgrounds from all these other things. So by looking at decays of charm mesons, because you know the initial state so precisely, that allows you a tool to filter out a bunch of stuff, a bunch of backgrounds that you might not care about. And so to make my point about these 2 things here, you see these 2 states. One here, the F2 1270, and the F2 1270 right here, and then the F2 1525, this really big, the dotted piece here is here. And you see that the F2 1525, F2 prime 1525 decays dominantly into K plus K minus. There's very little F2 1270 decaying into K plus K minus, but the converse is true for pi 0. So the one that's non-strange decays a lot to pi 0, and there's very little F2 prime 1525 decaying to pi 0. So by looking at decay patterns, and patterns of, you can separate out and sort of understand these sorts of things. So this type of measurement really confirms this type of prediction. This was post-diction in this case because this was known long before. So decay patterns are interesting. Okay, so where does GlueX sit in what is a really big global program of spectroscopy? And it really is. So I think you could take any particle, high energy physics or nuclear physics collaboration. There's probably some few people somewhere doing something related to spectroscopy within the collaboration. And so, I mean, GlueX is an emerging experiment. We're just getting started. We have a large data set now, and we are very unique in the fact that we have a high intensity photon beam for our probe. So it's a fixed target experiment. And in some ways, it's really complementary to things like COMPASS that has very high intensity pion beam data. And we're primarily aimed at studying light quarks, so things that are made of up, down, and strange quarks, whereas some of these other experiments have done a lot with charm quarks. So in a way, it's a different production mechanism and complementary in many ways. So the mechanism for GlueX is photon production. And as I said, one of the interesting things about that is that it's a photon beam. So the JPC of the beam is different than that of pions or kaons. So it's not a meson beam. It doesn't have 0, minus, plus quantum numbers. It has 1, minus, minus quantum numbers. So the beam looks like a beam of rho mesons or omega mesons or phi mesons. It's interesting then to see what types of things you produce in that case. And of course, we know that one of the big emphases of GlueX is to try to map out the spectrum of exotics. I'd argue that we shouldn't really focus on this is important, but we also really need the other things too, because these are going to be sitting amongst all these other states in the spectrum, and getting the patterns are very important. So if we find some state with exotic quantum numbers, it would be really important to establish those other states in the spectrum that have roughly the same mass with different quantum numbers. So patterns are absolutely critical in this. So here's GlueX. So some features of GlueX, right, is that it's going to be a very high precision experiment. And some people have had experience with high precision experiments in the past, and it starts to get really hard because you no longer become statistics limited in many ways, and you become systematics limited in your understanding of the underlying physics. So here are two good examples I'd like to show about complexities in physics. So this is a real Dallas plot, by the way. So it's mass squared versus mass squared. And this is d to k short pi plus pi minus, and if there were no intermediate resonances, pi resonances or k pi resonances, this thing would be completely flat and uniform. And so you see it's definitely not uniform, but even that, the uniformities are really non-trivial, right? So you can see right here there's a k-star band right here, and I know it's a k-star because the k-star is spin 1. You see there's a node here in the center, so the stuff piles up here and here. But you see where it's piling up here, this doesn't look like a nice reflection of this. Up here you have interference with pi resonances. So the pi resonances all show up on the diagonal. And in fact, this is probably the F2 right here on this band, I would imagine, because it's sort of pushed out. It's not uniform. So I'm assuming this is, this may be the rho, actually, sorry. Maybe k-short rho. I should have looked before. Yeah, this is probably the rho. In any case, the point I want to show is that the interference here is pretty wild, right? So there's destructive interference here, constructive interference here, and if you would try to just project this thing on one axis and fit it with bumps or something, there's no way it's going to work. And even fitting this thing with interfering Bragg-Wigners is going to be a real challenge. So you see all kinds of really wild interferences here. Here's a classic case that people have toiled over for centuries, well, not centuries, but decades, it seems like. The pi S-wave system, right? So this is notoriously hard to understand how many resonances are here. And this is a recent analysis of this system at high precision now in J-Sida case. And here's the S-wave amplitude, and there are all kinds of bumps and wiggles in this thing. And so how many resonances are there? How many 0++ waves are there, and so on? And these are hard problems, and when you start having large data sets like GlueX has, it exposes these types of problems, and you have to understand physics at a level that where you can sort of deal with these things. So things like GlueX, the challenges of precision analyses. I have a pion here where we could put a photon there also. It doesn't matter. These are the types of things you want to do. I mean, in your mind, you have a simple picture of photon maybe collides with proton, or pion collides with proton. It produces something, and then it decays this way. But what's happening here? What's that interaction? We don't really know. And building a better detector is not going to fix this, or understanding your detector better is not going to fix this, because this isn't something you detect. It's an intermediate thing. And then even more so, if that hurts, then there are things like this that in principle all contribute to, that you need to try to understand. And when we get to higher and higher precision, this stuff all becomes important. And I think that's why, from the outset, collaborating very closely with theorists and phenomenologists and developing a unified framework for both describing the data and analyzing the data is so critical to the success of GlueX. This is one of the challenges of precision analyses. So, summary. I'll summarize. Goal, I think. Use the really unique capabilities of GlueX to understand. Again, I hate to use the word qualitative, but in some ways that's really what you'd like to see. I mean, you'd like to see a pattern of states that just really convince you that hybrid mesons exist. I think finding one hybrid is never going to be sufficient, because somebody's always going to question, well, maybe that's a background, maybe it's not quite right. But if you can show that there's a whole pattern, and there's strange anti-strange hybrids and hybrids with charge 1, isovector and isoscalar hybrids, and show that the pattern all really matches, I think that's the real ultimate goal, and that's how you convince people that you understand that hybrids really do emerge from QCD. So that has to be the broad goal, I think, is understanding what classes of hadrons, and this is a whole new class of matter, effectively, what classes of hadrons emerge from QCD. And hopefully we can do that by exploring hybrids. And I think to do this, we have to be very, very systematic about how we go about it. One step builds upon the next, So we need an accelerator, detector, and beam. And fortunately now we have all that, so that's great. And we need data, and we have that now, which is really great. So we have lots of it. And now we have to understand and calibrate the detector, and we're doing that, and we're getting further and further along with that. And then the next step is to really figure out how to pick out individual reactions. So out of this whole mess of calibrated data, how to isolate a particular reaction that's happening. And at the same time you're trying to do that, you want to understand how you can extract something fundamental and useful about that. So what sort of model do we have that can be useful to tell us something that's fundamental about what's going on there, that's going to later inform either some other analysis that's important that will ultimately lead to understanding the spectrum of mesons, or you need something here. And basically then we need to iterate this, right? So we start with something simple and make sure we understand it, and then just keep building on this more and more complexity. And I think in all of this, having a robust software framework and this close collaboration between phenomenology and experiment is going to be critical to making this a success. And things like this workshop are vital to orienting people to, I guess, those that care about this and understand this in GlueX, what their vision is for how this would progress. So, yay, go. Go forth and learn.
We're working on it.
Yeah.
All right, thank you, Matt. Any questions for Matt? Good, very good introduction.
Good. I can sit down. Okay, thanks.
I think we're good. All right, Joe.
What do I plug into?
Blue is Ethernet if you want that.
No, I don't need that, but I do need something to.
Blue jeans, if you run the
No, he wants the VGA. You want to connect?
Probably
Oh.
the easiest way is if you just pull up the blue jeans and share your screen.
I don't know how to do that.
So, okay. See what cables we have.
If it's, we can just use the PDF if we need to. I'll just miss the animation.
Okay.